Hey folks, happy Tuesday. Hope you're doing well. I can probably close that. How's everybody doing today? Got a couple things on the agenda. We have, oh my goodness, I got too many windows open. Where'd you guys go? There we are. We're going to talk about the linked list lab, and then we got a little bit more linked list stuff to cover. We're going to talk about the positional linked list that we didn't get to yet. Remember, no class on Thursday. That's the wellness break. And then we've got the midterm on 3-1. Is that going to work, or is that like it's a wellness break? I'm feeling bad now. Is that going to be obnoxious to have to study for midterm over the break, the day you're supposed to have off for wellness? Because I don't think we need 4 whole sessions for trees. We could bump this a day or two if we wanted and do more review in lab on 3-1 maybe. What do you guys think? If we moved the midterm to 3-2 and then kept 3-1 as a study day, so use your lab time as a study day, I think that would be better. I'm thinking that might be a little bit better. That way you've got the whole Monday lab time set aside. All we got to do is study. And then we can do the midterm on Tuesday, and then we can pick up trees on Thursday. Okay, let me do that. I think that it's going to work out better. I didn't realize how we were stacking into the wellness break there, and I'm feeling bad. So let's go change that. So give me a second here. Let me go find the syllabus. I mean, if you plan on doing the midterm on 3-1 and you still want to do it on 3-1, that's perfectly fine. Like, you are welcome to take it on the first if you want to. I'm not going to tell you no, but I want to make it a little bit easier for you folks. So let's plan on doing it on Tuesday. And again, I'll still have the 2-hour time limit, so that should be fine. Okay, let's do that. So we're going to do midterm on 3-2. So what is this? Study. I don't know. No lab. lab Monday, midterm 3-2, and then trees on 3-4. Does that make sense? Do we like that? Okay. Oh, I closed I didn't want that window open. All right, so let's do that. So the no lab Monday is like study in lab. I don't know, study time. Study in lab Monday, midterm on 3-2, trees on 3-4. Okay. Then we've got a little bit more time because we have to do more linked list stuff today. So let's change that. We'll say linked list. Midterm review in lab Monday. Midterm review in lab Monday. The review Monday, midterm 3-2, trees 3-4. I mean, let's be honest. I think most people cram the day before anyway. I don't know if you're spending a whole week ahead of time, especially for an open book, open notes, open internet test. But that'll give you time Monday to prep, do your last minute, whatever you need to do. And I'll have the midterm open Monday and Tuesday. So if you want to do it Monday, great. If you want to do it Tuesday, great. I could be flexible there. So let's plan for that. Okay? Midterm. Trees. Okay. I like that. So I'm going to save that. Oh, I should have saved that as like a V2. I'll do that in a second. Let me find that window again here. Go back through all my folders. Sorry, folks. 2021. There we go. We'll save that as a V2. Oops. All right. All right, and then I'm going to go update that in Canvas here. Let's go back to files. Drop that one in. And I'll just add it to the module. So I'm going to remove this link. Let's add a new. Did it not upload? It didn't upload, did it? I uploaded the wrong thing. Nope. Okay, yeah, I uploaded the wrong thing. That was my bad. I didn't copy the syllabus, I copied the other thing. That's why I can't find it. All right, let's try that again. Yeah, it's not the V2 quick start. Delete that. Okay. We want the syllabus V2. Then we can go fix it in the modules. Add V2. All right, I'm just going to take off one. We don't need it there. I'll delete it, remove it, sure. All right, cool. So now we got V2 out there. Hopefully that will make life a little easier here. We can just work on linked lists today. I did post the midterm review. I think I added an announcement for it. I did it right. Yep, the midterm review. Is it not a link? It should have been a link. Yeah, there. So the midterm review, that was last time. We're going to have 15 quiz style questions that are true, false, short answer, like fill in the blank, this sort of thing. You know, tell me this, like a 1-2 liner thing, and then 3 longer program questions. So we can go over that Monday if you have questions, or you know, maybe even later today. I'm not sure. We'll have time. We'll see how we go. Okay, so we're going to work on the lab first. So the idea with the lab, following on the text, is we wanted to use those sentinel nodes. So we didn't have a none head and a none tail. Because the idea of having to have these, we had lots of extra special handling for doing things where we checked if head was known, we had to do things, we had to set tail to things. I mean, it's, you know, if this was not none, set it. It got to be obnoxious to have all the special handling. So using those sentinel values, we can make this code a lot cleaner here. Now to do that, we actually, I prefer it with a circular linked list at that point. So you have one sentinel node, and that's what I asked you to do for lab. So it wasn't exactly following along with the text, but kind of in that idea of following along with the text. So we're going to change this to our, I don't know, head. Well, I don't call it head. And so it's going to be a self node. And now here's the fun thing. So self node, it has a none for data. Okay. Then what we want to do, that's this is our dummy, or sentinel, right? Sentinel, head, tail. It's both. And then we're going to take self head, and we're going to say its next value is self head. It points to itself. And then it's self head's previous points to itself. self dot head. So what we're going to get here, let me pull up the whiteboard. If I can get this to cooperate. Whiteboard. There we go. Let's see. Maybe we'll get it here. Oh, did you guys see? I don't know if you can see it well on the camera. They discovered a new element recently. It's AH exclamation. Oh, can you see there? Am I up high enough? There we go. It's the element of surprise. So our linked list here has none for data. Its previous is itself, and its next is itself. That's how we start. What this is going to let us do is we always will have a reference to previous. There's always a node there. And hey, thanks so much for dropping by. Ian Star. That's so cool to hear. And then its next is itself. So we always have a node. We never have to worry about is my next none or is my previous none for any of those checks, because we're always going to have a value there. And that's the point of having the sentinel value here. So what we want to do to add to front, we don't have to do any of this if self head is none. We don't do any of that. Right? All we do is we say, take the new node. It's a new node. Right? It has the data. Its next is self head, and its previous, what comes before it, so its previous, is going to be the self head previous. Right? Because if we're inserting ourselves at the front, our previous, is going to be self head as well. Right? Hang on. So if we want to add to the front, right, we want to become the new front node. My previous needs to be head, the dummy head here. Yep, that's it. So my previous is the self head, and the thing that comes after me is what came after heads next. I'm working on the Python courses here, yep. So I've still got the previous one in YouTube, and I've got this one here. So what we're doing then, no matter what we have in the list, our previous will be the dummy head node, and then our next is whatever head's next used to be. Because head next would be the first item. So in this case, the first item was itself, so our next here is also going to be this one. Okay, so we're almost done, but now what we need to do is we need to fix up the link. So now our next previous needs to be us, because we're the end of the list. So we got to fix it up. So our next previous, let's see. So our next is what came after head. And then our previous next needs to be us. So self dot our new node previous previous. Its previous next value needs to be the new node. Right? So we're putting ourselves in, like we're dropping ourselves in. We're going to be between what used to be the front and the head. Right? Our next is what used to be next, and our previous is the head. Then we need to fix up those connections. So our previous next is us, and then our new node's next previous is us. Okay, and this is going to work in all the cases. So if we had a bunch of data in here, right? So if we had, this was the head. This is like the dummy head, the sentinel head, right? The first item here would be this thing. And then maybe we had a second item was this thing, right? And they're all doubly linked. They link to each other. And then the last one links to the dummy head. And the dummy head previous links to that one. So the dummy head can always find the first node and can always find the last node because it's doubly linked. And then we're circular in this case. So then if we wanted to become right here, right, we're going to put ourselves in. We're going to say, okay, my previous is head's next previous. Right? My previous is, I'm sorry, my next is head's next, and my previous is the head, because I was the front. Right? What comes before me is going to be this dummy head thing, And what comes after me is what head used to come after, or what came after head. So head's next is my next, and head is my previous. Then we need to join ourselves back up in the link, right? We need to fix these links here. So my previous next needs to be me instead of this one. Take that one out. And my next previous needs to be me. So my previous next is me, right? Previous next is me, and next previous is me. We're putting ourselves in the loop, so we're connected, and then we're connecting those ones to us. And there's no special handling. And this will work if we're empty as well, right? Let's look at this empty case again. So the empty case here, let's erase all these, right? If we're perfectly empty, its next is itself, and its previous is itself. So we're going to add a new node. We're going to say my next is what came after head. So head's next is my next. Okay, so my next then, head's next, oh my goodness, whiteboard. There we go. So head's next was itself. So my next will be head. My previous will be head. Okay, now my previous next points to me. So I'm going to break this link here and say previous next is me. And I'm going to say, hey, next's previous is me. Previous is me. Right? So we've fixed up the links here, and it works in every case, which is the beautiful part. That's why I like these circular, doubly linked list with this dummy node or the sentinel node. Okay, so add to front works. Add to back works the same way. We don't have to deal with any of this nonsense here. Right? Now we don't have a tail anymore, right? What we have is head's previous is always the tail. This is always first node or itself if it's empty. And head's previous is always the last node or itself if it's empty. Right? Head's next is the previous head, and head's tail is the previous tail, or head's previous. So if we're adding to the back, now what we're going to do is we're going to make a new node at the end. So the current end, right? The current end, so if we look at this one here, its next is the head node. The head's previous is that node. So my previous then, when I make a new node here, new node, it's the item, its next is going to be self-head. Okay, my previous, what comes before me, is the thing that head used to have before it. Head.previous. Right, so we're saying, if I want to put a new node here at the end, right, I want to be here, my next needs to be the dummy head, boom. My previous needs to be what used to be head's previous. So head's previous is this one, so my previous is here. I put myself in, now I need to go fix my links. My previous next needs to be me, my next previous needs to be me. Right, so these same two lines here. Right, my previous next is me, and my next previous is me. Right, that's going to go fix those links. So it's going to say, okay, hey, previous, you don't point here next, right? You no longer point there. You now point, oh my goodness, you point to me. And then my next previous, hey, you don't point here anymore. You don't point there, you point to me now. Right, so it works the same way. We're just putting ourselves in between those two nodes. So we added the front, we added the back. Now removing back, we can change all of this handling, right? We have a, we had a self number of items, didn't we? Oh, we didn't have that. So they define the length. We're going to return self.number of items. Right, and then maybe we have a is empty. Return self.number of items equals 0. If it's 0, we return true. If it's not 0, we return false, we're not empty. So we can check if we're empty, if self.isEmpty, raise a value error. Otherwise, okay, we don't need to do any of this stuff now. Right? So the data is, the back of the thing is my head's previous data. Right, heads previous is always the last node. So grab that data. Okay? Then set heads previous data to none. Okay? No, we don't use pandas in this one, sorry. This is just a computer science fundamentals course. You learn all about pandas in the data science courses. Okay, so we got the data out. Now we need to take ourselves out of the list. And we don't have to do any of this nonsense. Right? To take ourselves out of a list, we take our previous, right? Set its next to my next. Take our previous, set its previous, or take our next's previous, set it to our previous. Takes us out of the link, so no one looks at us anymore. So self next's previous is equal to our previous. And now this gets a little bit silly here, but that's okay. So it's not next previous. It's so self head previous is us. Let's do this. Let's define that as like node to remove. Node to remove. There. This will make this a lot cleaner. Okay. Node to remove data. Node to remove data is none. Okay. Then our node to remove's previous. Its previous value, its next, we're going to change to be node to remove's next. And then our next's previous is going to be our previous. Right? We say take us out of the list. Right? Takes us out of the list. And now they're no longer pointing at us. We changed its links. And this one doesn't point at us either. One of those ones there. Okay, so we're out of the list. We're done. Removing from head is the same process. There's no special handling because we always have a node. So again, we do the same thing here. Lone Star. Okay, yeah, with an L. Nice. Yeah, thanks for dropping on by. So now the node to remove is not heads previous, it's heads next. And that's the only thing that changes here because we're removing the front node. Oh, that should be a colon there, shouldn't it? Hey, that's so cool. Yeah, what are you working on in .NET? Now, if you can share. Hopefully fun stuff. Okay, so what happens for us now is all of our code handling is identical for removing and for adding, right? We just add it in between two things, but we always have the thing because we have that sentinel value. Lone Star, I got it, yep, Lone Star. Okay, so popping an item here, right? So we still have to walk current item. So we're going to take, we're going to leave current item is self head next, right? Because that's the first thing, and then we're going to walk the given range to take current item data, current item's previous next is my next, current item's next previous is my previous, and we don't need to do this checking for tail either, because you know it's just going to work. Okay, so the doubly linked list makes a lot of this easier now, at least in terms of code. Okay, what we haven't done yet is we haven't figured out how to get particular items out. Right, to say, hey, I want this item, I want the next item, I want the next item, I want the next item. Do one of those iterators. We did that a while back with like our very first lab, where we were working with like the geometric progression, where we were iterable, that sort of thing. Right, we can iterate over that way. So let's go find that code here. And we want 2001, there we go. Let's take a look. See if we can add an iterator. So we can just do a for loop for us here. That was lab 1. Oh, lab 0? Was that lab 0? It was lab 0. Okay. And so an iterator is ourself, and we have a next method here. Okay, so we're going to copy those two here. Let's see if we can add those in. Move front, pop a given item off. Okay. So we are the iterator. We can iterate over ourselves, and we want to keep on iterating as long as our, so we need to have a current here, right? That's the problem. So let's see. So when we want to iterate over ourselves, we want to set self.current is equal to, we want self.head.next. Oh, an autospy, very cool. Yeah, ASP, APIs, MVC applications, console apps, awesome. Ooh, TypeScript is fun for JavaScript, and SQL is really good. Yep, that's good stuff. So as long as our self.current.data, you know what? If our self.current is self.head, let's do that. Then we stop iterating. So if our current becomes our head, which our head's next might be ourself, right? Might be ourself. Otherwise, what we want is our current's data, and we don't want to advance, right? What we're going to do is we're going to take self.current equals self.current's next. Right, move to the next node. So we should be able to walk the nodes here using this iterator. Let's give that a shot. So see if we can make a little doubly linked list here. That was all singly linked lists. Let me just comment all that out. Code, comment. There we go. Let's make a doubly linked list. So doubly linked list equals a doubly linked list. And then for, I don't know, so n in range, let's add 10 maybe. Doubly linked list dot add. You want to add to front or add to back? If we add them to the front, we should get in reverse order. If we add them to the back, we'll just get in regular order. We can add to back. Right? Add to back the n. Okay, and then we want to say for item in doubly linked list, print the item. And let's see if it iterates, right, from front to back. Let's see if this works for us. Uh-oh. Oh, now we have no previous. Oops, that's right. So our add to back, we messed this one up. So our next item is self-head, and the previous item is self-head previous. Head.previous. That's right, we forgot to change that one. This is why it's good to test it, right? So if we add it to the back, what is our previous is what used to be head's previous, and our next is head, because that's the last item. Okay, let's try that. And we get our items, 0 through 9. Right, so we're able to iterate through them using our little iterator here, where we start at head next, and we go until we hit head again, because it's circular, right? We should expect to just go around the loop until we go back to head. Okay, so we can add a little iterator here for fun. That one I don't think was in the assignment, but this is all fun to add in here. Okay, and again, when we look at these, the performance of these now, right, to pop a given item out, we have to get to k index. Right, let's look at add to index or insert, right? We could add an insert. So let's add an insert. Let's call this one insert. An item at an index, add an index for a given item. Okay, so we're going to start at the front and we're going to walk until we get to where we are, right, to whatever index we want to be. Wow, why is that still highlighted? That's obnoxious. Why is that still highlighted? Oh, awesome. This is essentially just a Python class. We don't get into much of the fun data science stuff till later in the program. If you remember from your program, Lone Star, you took like 150 and 200. This is essentially those courses, but taught in Python. So we tee up some interesting concepts, and our project is much more interesting than you would do in C++. It's a little bit stats-based, but we don't get into any of the actual fun data science stuff, unfortunately. Yeah, there's lots of good content out on the internet. I've got a couple good courses that I liked. Okay, so again, I don't know why it's highlighted. That's really weird. Okay, sure. So insert is still going to be O of k, right? Whatever index we need to get to, right, is where we're going to have to go. And now if we want to be index 0, right, that's going to add to front. So we're going to range nowhere. So we're just current item is heads next. So whatever our current item is, we want to come before it. Okay, so we don't need to do any of this stuff here. And this is insert an item is going to be +1. So once we get to the current item, we want to come before it. So we're going to take a new node, is a node, self.node. Given the item is our data. And then what comes before me is the current item's previous. I'm sorry, what comes next? So this is next equals is the current item. And what comes previous is the current item previous. Okay, so we get to where we want to go. We've got to that item. Now we're going to put that as our next, and our previous will be its previous. So at node 0, we don't walk at all. We just start with the head next, and we put ourselves in there. And then again, we do our fix up here. So our next item here, new node. Where is it in here? New node, there. And then we put ourselves back in the list. Okay, our previous next becomes me, and our next previous becomes me. Okay, now you probably noticed we have this code in here a lot, right? And I feel kind of bad about that. Could we do better? We can do better, right? We can do better. So let's make a private method for this, right? Why not? So what we want to do, right, is we are going to say insert between. So we're going to add a function here. Well, let's make it private because we don't want other people calling it. For insert between. Define private insert between given the item, the previous, and the next. Okay? And we're going to take all of this code. We're going to say, okay, new node is the item. My next is the next. My previous is the previous. Set my previous next to me, set my next previous to me. And we put ourselves in between. So now instead of doing this every time, now what we can do is we can call insert between. Self.insert between. All right, here's our item. Our next, I'm sorry, our previous then, right, is our current item's previous, and our next is the current item. So I'm gonna name these two. So this is previous, just to make this clear, because this can get kind of confusing. So using positional arguments can be a little awkward sometimes. We're going to insert between, right? So anytime we have to do that, we can insert between. So this one's not an insert between because we're removing. Removing, that's not an insert. We could have a helper method for remove. We could definitely do that. All right, Eric, which part here? For our helper method? How we're inserting between nodes? Oh, okay. Yeah, if you want to check out the VODs or Exclam YouTube, you can actually start the course from the beginning if you want it to make a little bit more sense. And this is actually the second course in a 2-part track. So you might want to start with 1501 first, which is like Intro to Programming Python. And then this course is the second course in the track, 2001. So we're inserting between our nodes. So the same thing here for our inserts then, right? When we add to back, now we just want to call, instead of doing all of this, we're going to call self.insert between. Insert between. Here's the item. Our next is self-head, and the previous is self-head previous. Look at that. I can just copy paste. I love when I can copy paste. And it puts it between head as its next value and head's previous as its previous value. And then we'll fix up its references. Same thing goes here. Right? So this is just self.insert between. Insert between, given the item, next is self-heads next, and previous is self-heads next. Right, so you see we're kind of simplifying our code here too, which is awesome. can I actually do this? Can I reference myself here? I don't know if I can do that. Maybe I can do that. No, it doesn't like that. Okay, never mind. Didn't think I could do that. Okay, I was trying to clean that up, but... All right, so let's try cleaning up our removes then, right? Remove works the exact same way. We find a node to remove, we remove it. So we want to have a remove node. So insert between then should actually do our self.number of items plus 1. Right, when we add, let's do that. So that way we don't even have to remember to add items. Right, any code we have in here more than once we're going to feel bad about. How clean this is making this. This is beautiful, isn't it? It's beautiful. Okay, so now we're going to clean up the remove code. Okay. So why is that still oh, is it it's tabbed in too far? That's why it was highlighted. It's like, no, that's a stupid method. Okay. Thank you. It was telling me I was doing the wrong thing and I wasn't paying attention. Okay. We got insert between, and then let's do a remove. Data. Oh, we don't need to return anything on an insert, right? Okay. One more. So we're going to do a remove node. So we're going to define, oh, not there. Let's go down here maybe. Define remove node. Yeah, go. Thanks. Okay, so that if we remove a node, then we're going to do this thing. So we still need to go walk and find the node. We're going to do this process here. So actually here, if let me give you the shortcut. We can right-click here and say refactor, and we want to extract method. I'll just remove node. Okay. And oh, and it even said, hey, there's 2 code fragments that can be replaced. We'll do that later ourselves. Okay, so here's remove node. Okay, here's the other one. I'm going to remove that one. It generated this one for me. So given a current item, it takes the data, sets the data to none, sets the previous next to my next, sets the next previous to my previous, takes out item by 1, removes data. Perfect. I just want to move it down 1 here because I want all the private methods to be at the bottom, and it's just a convention. In different organizations will have different conventions, but typically you want public stuff at the top, private stuff at the bottom. Okay, insert an item. Great. Oh, we were removing, right? So pop, we have to walk, and then we remove the current node. Okay, so remove from front then. Maybe we should do this here on our, let's put that in there, right? In our remove node. Never mind. I'm feeling bad about that now. Should we? Because we have different checks each time. We'll just leave it. We'll leave it. So the node to remove then is self head next. So that's all we have to do then is call self.remove node given head.next. Self.head.next. Self.head.next. Right? Remove the front thing. And we're going to return whatever that gives us. Right? Awesome. And remove back does the same thing. Right? We're going to return, oops, self.remove. And what we want to remove is head previous. Boom, done. So these really clean up super nicely here. Yeah, Python is great. Python is a great language, not only for data science, but for other tasks as well. For sure. Okay, so we're just trying to clean up the code. So pop needs to walk to where it goes, insert needs to walk to where it goes, and then we'll insert between, right? Insert between and remove being helper methods. These are public. They should probably go up a little higher. Just trying to clean this up so it's pretty. Okay. All right, and I think that's it here for our doubly linked list with the Sentinel head. And a circularly doubly linked list with the dummy head. So this is actually a whole lot cleaner then, right? This is less code than it was before, and we've even added more features to our previous version. So let me check GitHub here, and we'll go commit this version. And then I got to step out for just a minute or two to get my daughter set up on her piano lesson. We'll take a quick break, and then we'll come back. 2001. Here we go. I'll put some music back on for you. Let's see, do we add more code or remove more code? There's a bunch of red, there's some green, some red, there's some green. It's hard to tell. So what's fun, here, this is doubly linked list, circular, doubly linked list with Sentinel node, random capitalization just because, why not, right? I don't know why I did title casing. And we're just making this doubly linked list. We're looking at introductory data structures and how we would do them in Python and their performance. I previously said the performance of oh man, it's locking up now. Come back. Is it the music? I don't know. There. So insert, you just have to get to k index. The insert itself is super fast, right? Next is just one operation, right, to iterate over itself. Insert between, constant, remove, constant, once you get to the node. And that's the problem. So that's what we're going to look at next, is that positional linked list and how we can keep people using our list interacting with a position wrapper so that they can hold on to a position and do operations around that position, which really gives them good speed for our data structure here. So we'll take a quick break, and I'll be back in about 10 minutes or so. Let me put up our break time screen. Okay, so we'll come back, say, what do you think, 4:22 p.m., 10 minutes, and we'll go from there. All right, thanks, folks. I'll be back in a minute. Hey guys, just looking up the book info here for our friend. Let's see. Here we go. Nightbots. Oh, I can talk. I don't have to chat at you. I'm back on back on mic here. Yeah, the player's guide was fantastic. The guy who wrote it is working on a 4th version with the latest and greatest C# and .NET Core stuff. So he's been having pre-release information out. He's hoping to release it soon, and I'm super excited for it. I'm bummed it wasn't quite ready yet, but I mean, he's basically done a whole rewrite. And for $30, that's a fantastic book. Fantastic book for sure. All right, so we're gonna work on. Oh, we can pause this here. We're almost done. We're going to work on this positional wrapper next, where the people using our data structure get to interact with positions. So that takes it to the next level. So we don't want to have to expose them to nodes, because nodes are really obnoxious, right? Like having to work with the node and next and previous and data and all those things are not ideal. What we want to do is we want to add in this idea of a position so that they can be at a given position in our linked list and add before the position or add after the position and not have to traverse all the way to that n item all the time. Yeah, there we go. All right, and yeah, Lone Star, not that, you know, just Google. I'm sure you can find a PDF around somewhere. Not that the author didn't do a nice job, but and shouldn't get paid for it, but if you just want like a quick reference, you can find it on a quick Google. All right, so I'm going to pull up the positional linked list. That's section 7.4 in the text. We got through 7.3 with the lab. Any questions about the lab before we move on, by the way? With the circularly doubly linked Sentinel list. And I didn't bother writing all of these base classes like he did. So he wrote a base class that does certain things, and then he extends his base class, which is great, but I find that more confusing as we're trying to learn these things. So I just tend to kind of skip that, and I don't bother with it. So that's my way of cheating through it, if that's okay with you guys. All right, so we're going to wrap up our positional piece here. So let me grab this one. I got to throw it to the side. And the idea is that we will actually give people access to the position class. So it's telling them, hey, that you can get the data out of it. You can get the first position or the last position. You can get the position before this position, the position after this position, that sort of thing. And then you can add before a position or after a position, or replace the data at a given position, right? So we can just kind of work its way through. Let's see. And he uses all this extra, the wrapper classes, and I'm not going to bother with that. If you like it, great. Let me just maybe copy paste this, so we can leave this version here, or it's probably fine. It's probably fine. So what we're going to do is we're going to write a class position, and this one is meant to be usable by the other by people using our class. So position has an init method that takes the container and the node. So it's a position is a wrapper around node, is what it does for us. So it's gonna, numbers makes your head hurt. Yeah, sorry. So position wraps around node and gives people access to the private node through public methods, which is pretty cool. So it's going to take self.container is the container. The idea is we can say a position belongs to a given list, and we're going to use that for validating later. And self node is the node. Okay? And then define, he uses element. Element. I like data. Sure, I'm going to use data. He's going to return self.node.data. Node, I think it's data, right? Node data. Let's check the node class here. Yeah, nodes data. We're going to return data. Okay? And then we can define a equals to method. So we're going to say, hey, this one equals another. So we're going to check if the type of other is the type of self, right? Do they match? Are we the same type? Are we both positions? And the other node is my self node. And we're not even using equals. We're using this is operator here to say, hey, you have the same reference here. That's what is does. Remember, it doesn't check equality. It checks, do you have the same reference? So if your node references the node, right, we must be equal. And we don't care about this warning, right? It's a protected member of the node class. Yeah, that's fine. Right? It is us. So others node and my node. If those equal. And then not equal is the opposite. We're going to return not self equal other. Self and other. Oh, not neg. Not equal. Self equals other. So it's the opposite of this, right? Is we already define equals, we can tell you if we're not equal. Yeah, the class. So the class is essentially this particular noun. It's a consolidated something that we're going to write that has attributes and ways to interact with it through its public methods. So that's the idea of encapsulation. We're encapsulating all the details around this class and putting them into one spot. And then the class is responsible for maintaining itself. Okay. Oh, my phone. Sorry. It's going loud. All right. Sorry. Yes, piano lessons, good. Sorry. All right, we are good. We're good. Okay, so we've got positions then. So what we're going to do, we're going to add some helper methods here for our doubly linked list. And again, I like these down at the bottom. The book has them up at the top. I don't know why. It doesn't really matter too much here. But I'm going to put them down here. We're going to have define a helper for validate. And validate takes a position. And he uses like P all over the place instead of position, and it's not hard to type position. So I'm not a fan of how the book writes some of the stuff. We're going to check if not is instance of position and self.position. Lowercase self.position. So if it's not the instance of is instance, there we go. I think I typed it wrong. I'm going to raise a type error. And again, I don't need to add any extra text here. I'm not going to bother. I'm going to be lazy because I don't care. Right? You could add in the proper error messages if you want. And then we're going to check if the positions container, is not self. There's a value error. Right? So if it's the container that it belongs to is not us, it's not a position in our list. That's a problem. Okay, and then we're going to check if the position dot node, and it says we use dot next is none. We'll raise the value error. The idea here is we will set its next to none when it's no longer a valid position. Otherwise, what we're going to do is we're going to return the positions node. So anytime we are handed the position, right, if we want to add before or add after a given position, we can validate that the node is valid inside of it. Right? It is a position. It belongs to our list. It hasn't been invalidated. We can give them back the node. So this is just a helper method we're going to have inside of our class. Right? We're going to add another helper method for make position. Make position. Given a node. So we can make a position out of a node, or we can turn a position into a node, right? One way or the other. So we're going to check if our if node is self.head. We're going to return none. none. Okay, so if we are the dummy head thing here, if we're the sentinel node, that's not valid. Just give them back nothing. Otherwise, we're going to return self.position given the node. Oh, and self, sorry. Self is us, right? Because we are the container. So position wants a container. That's us. That's self, our linked list, and then the node itself that it wraps. Okay, so we got those helper methods then. Okay. So then what we can do, now we can add ways for them to interact with us, right? We can have a define first returns self.makePosition out of self.head.next. Right? So it'll be our first item. And we're just going to give it back as a position. So this way they can get the first position in our linked list. We'll define a last. Right? Does the same thing, but it's head's previous. Okay? Because we don't use the tail like he does. Right? We just have this linked list here. We just have our head's previous as the last item. Okay? And then we can define after a given position. So if you give me a position, I'll tell you what comes after it. So we're going to have a node is self.validate the position. Right? Make sure it belongs to our list. Make sure it is a position. Make sure it belongs to our list. Make sure it hasn't been set next as nothing. If that's true, then we can return self.makePosition. Position of the node.next. Okay? We do the same thing with previous. Make sure it's valid, and then give them my previous. This is before. So if you want what comes before or what comes after, right, we're just going to walk in one direction or the other, making positions, right, validating the node, making positions. Okay? And it might be none, right? Because remember we checked when we did our make position. Our make position says, hey, if we are the dummy head, the sentinel value, they just get nothing back. Right? It's not usable. Okay, so we got that. And then we can then now, if we wanted to, for our iterator, we don't need to give them the items directly. We can iterate over positions, which is fun. Okay, so our iterator then is different. So what we're going to do is we're going to actually change this up a little bit. So we're not going to use this next operator. We're going to do our own iterator function here. So we're going to say our current is self.first. Give me the first item. And while current is not none, we can do something. Now there's a really cool keyword here in Python. It's yield. And yield says give me the first item out. So current.element, here. Oh, I'm sorry, we called it data, right? Current data. Give them the data when they're iterating over. So give them the data here. And yield says wait until they ask for the next one because we're iterating. And then when we're done, we're going to say current equals self.after current. We're going to use all that positional wrapper stuff to loop through with a quick little iterator. So let's make sure it still works, right? We added some features. Let's run. Oh, node has no next. Right here, nodes next. Dot next, that's right. Not lowercase, or not an underscore. Try it again. Okay, so we can loop through, right? Again, using that positional if we want. Right? Or, right, we can say we want a current position equals our doubly linked list dot first. And we can do the same thing here. We can say while current position is not none, we can print current position dot data. Right? And then we'll say current position equals the doubly linked list dot after the current position. So we could do the walking on our own side if we wanted to find a particular value. Is not none, not in not none, is not none. So this will do the exact same thing, right? We're going to iterate over it our own way because we have access to the position now. This is our iteration using position here, or using the iterator here. Sorry, that's this one here. Or this is using the iterator. Okay, both ways work. So if we want to go find a particular value, we can traverse the list with this before and after. Right? We could do it in reverse as well if we wanted to. We could take the last and go previous. Right? We've got lots of options. Right, so again, adding first, adding last. Now adding before and after is good. So now we can give them the ability to add before and after a given position. So if they give me a position, I should be able to add before and after it. Where are we doing some position stuff? Oh, I did a copy paste, sorry. There we go. So first and last with before and after. Insert. Okay. Good so far. So we want to define insert or add after. Add after if you give me a position and the data. And he uses P and E, and that's obnoxious, which is, fine. So what we're going to do then is we're going to validate the position. Right? So node equals self-validate position. Make sure it's valid. Right? And then we're going to self.insert between. And what we want to insert between the node. I'm sorry, we're going to take the data. Its previous is the node, and its next is the node.next. Right? So that'll insert between. And insert doesn't give us anything back, right? Insert between. Where do we have that? Yeah, it doesn't return anything. So maybe we could return the new node. Let's do that. That'll make this a little bit easier for us. So if we return the new node, we're going to insert between. And we're going to return self.makePosition out of the node we just made. Okay, so we insert between where our previous is the node, because we want to come after that node. Right, after this position, and the next is what that node's next is. It's going to fix us up, and then it's going to make it into position and give them back. So it's going to give them back the new position. Okay? So define add before. Again, same idea, position and data. We're going to do the same thing here. But now our previous is node's previous, and our next is the node. Right, we come after. Okay. So we could delete a given position. We'll define delete a position. Right, we're going to remove, right, this remove node. Right, we have a remove node option here. So we need to validate first. So validate the position, and then self.remove node given the node, and we can return the data, right? We'll do it one last time because that returns the value that was there. Let's return the value that was there. Okay. How about replace? If we wanted to replace the position with some data, we need to validate, right? Validate the node, and then we're going to set old or original, original, sure. Original is node.data. We'll set node.data to the data you give me, and we're going to return the original. Original. Probably should spell it right. Okay, so I can replace a given value there. Right, so now we have options for working with this list given positions, and we can interact with this linked list just using this position class, the public position class. Right, so it's a positional wrapper around the linked list. So that way, if someone's working with our list and they want to say, I think one more, if they have a lot of inserts and deletes, so I was happy with one, right? We know that inserts and deletes are actually really slow in an array-based list because everything has to shift. But with a linked list here, once you have a position, inserts before and after, constant time, right? We just have to add the node, change the links. We're done. So if we look at these, the speed of these things then, right, to add after, right, this is O of 1, right? It's constant, right? Adding before, it's constant. Deleting, constant. Once you have the position, you're done, right? Before, constant. After, constant. last, constant. First, constant. Right, replace, constant. We know where we are. Add to front, still constant. Add to back, still constant. Remove the back, constant. Remove the front, constant. What is slow is getting to an index. So you have to iterate over the list to get to where you want to be. Then once you're there, you can add, subtract, add, subtract, add, subtract any way you want. And there's never any resizing that has to happen of the array backed storage. Okay, so that's our amazing performance here of a linked list. And these things are real helpful. We can use them certain places, right? If we know we're going to have a lot of insert and delete operations, great, we can go for it. And again, if you have to like start at the beginning and go find to where you need to find it, it's slow because you have to, every time you have to walk a node, it takes one operation, right? So the more ends you have to walk, the longer it's going to take. So something like a find or an index of or something is still going to be slow because you have to look at k items, whatever index it shows up as. You got to be careful there. Let's see, what did we? That was the in operator. We could check if it was in, or we could remove something. It would take k. The first time we found that item there. So there's still a couple things that are slow. It's not fast everywhere, right? But it's relatively fast, right? And there's a really cool case study you can look at where they keep frequently accessed data at the front of a list. Right, this is like move to front heuristic. So the most often thing that you access out of your list moves to the front. So you have the least amount of walking to do, which is really cool. And it's really fast to swap items. So he goes through that. That's really fun to look at. And then section 7.7 looks at a comparison between array-based and linked-based lists. That's kind of what we've been talking about. Right? So that's about the end of linked lists. I think we're good there. I did want to show you here then. Where is it? Oh, I closed it, of course. There we go. Don't forget project 2 is coming up due. I'm sorry I haven't had a chance to grade your project 1s. That's on my list to do. I should get that done this week, I'm hoping. I apologize for the delay there. And then I'll post a quiz for the linked list chapter coming up. And then that will be all of the material for the midterm. So chapter 2, chapter 4, chapter 5, chapter 6. That's what's going to be on the midterm. So we do have the practice midterm out here. You can link it from announcements, or it's here in the course files. So this was last year's midterm. I just printed it right out of Canvas, so that it's a little bit ugly. Like, it's huge for being 12 pages. I'm sorry. Right. So like, how does a position wrapper in a linked list allow for move ahead operations to run in O of 1 constant time? Well, what is that position wrapper doing? It means we know where we are. Right, so add before and after, super fast, because we're already at that position. Talked about UML. We haven't done that as much this class. I'm sorry, usually we're in the lab and we have Visio and all sorts of good tools. There's other ones online. You get 3 sections. You get the name of the class. You get the attributes here listed with usually their type, and then a methods section. So it's 3 sections. It's name, attributes, methods, and it's a common way of representing a class. And then write a unit test. So unit testing definitely included on the midterm here. That was like this was a slightly longer one here. I kind of took that as 2 parts. So like that would be like one of the programming questions, which you'll get 3 of. Purpose of unit test, that's a short answer. I'm using O notation, that big O notation. What's the average time it takes to remove an item by index in a linked list? Right, by index. Write a function. So this is one of the longer ones. Sum of values an even product of indexes. It returns the sum of all values and indexes whose product of row and column index is even. So the row index 0, column index 0, right? So none of those are going to be, 0 is not even, right? I think 0 is a nothing, but 2, 2 here, right? So 0, 1, and 2, so 1, 2, right? Here, oh, here's the indexes, right? I just named the indexes. So 0, 0, 0, 1, 0, 2, 0, 3. So 1, 2 is even. 2, 1 even, 2, 2, and 2, 3. Right, so then you would sum those together. Just working with a 2-dimensional list, having fun with it. When the following principles of abstraction, oh, you can't even see that question, I'm sorry. Oh, maybe we can copy it. I think the text is there. Abstraction encapsulation, yep. So following the principles of abstraction encapsulation, we what? What does that mean when we're following those principles? About hiding our data, having private attributes, public methods, that sort of thing. Write a recursive function, sum of ordinal values in string, given some string, returns the sum of ordinal values of all the characters. Remember, you can get ordinal of a character to get its ASCII value back out, and specifically do this recursively here rather than iteratively, just for some fun practice with recursion. Describe the process of designing a solution to a problem. What do you decide what classes to create, what attributes and methods they will have? Right, about object-oriented design, right? The nouns, their attributes, and their verbs, that sort of thing. An iterative function, sum of ordinal values, right? An iterative version of it. And 3 reasons inheritance is useful for programmers. What happens when you make a copy of a list? True or false? Can have many base cases. And using O notation, what's the average time? Oh, what's the rest of the text? Looks like you can select it there. I don't know why that toolbar printed. Time to look up an item by index in a dynamic array, a list. Okay, and that's it. So you can expect 15 short answer questions, 5 programming questions for a total of 30 points. So half the exam is the short answer questions, fill true, false, if false, correct the statement, and then the other 3 questions are going to be programming questions, 5 points each. So the points are a little bit funny on this. Don't worry about the point values here. So it'll be 30 points overall. Right? Each one of the programming questions will be 5 points, like write a class, write a unit test, do something with 2-dimensional lists, do something recursively and iteratively, that sort of thing. Okay, so that's what you can expect for the questions. We can go over this on Monday if you want during lab time. I wasn't planning on streaming, but I can if you guys want, or if you have questions about it, just shoot me a message anytime. We'll reserve Monday for study day, and we'll do the midterm on Tuesday. Does that sound good? I won't ask you to write any UML. I might say, hey, write a class and it looks like this. Does that make sense, Grenjits? So I think it's understandable, but I won't ask you to write any yourself. Cool. So like the one long answer will be write a class and a unit test. One will be recursive and iterative, and one will be 2-dimensional lists. So let me update that announcement so you know exactly what you're getting into here. Here, I'm going to update this one. Edit. Come on. Come on. There we go. One on classes and unit tests. One on recursive iterative functions. One on 2-dimensional lists. Okay, so that's your 3 long questions here, specifically. It's open book, open notes, midterm. It's open book, open notes, open internet, but not open friend, neighbor. Okay? Yeah, sum of ordinal for I, and yeah, definitely. That's a great iterative solution, robot. Yeah, it's super easy. Making you do it recursively is kind of silly because like you're using recursion essentially as the loop in that point, which is, I mean, if you can just loop with recursion, you can usually do it iteratively without much trouble. It's not something like the backtracking where recursion is really helpful because it's managing all this state for you. Okay, I think we're about out of time. Should we see if anyone is around to raid on Twitch for fun? Let's see who's around. Let's see, there might be people in the Knowledge Fellowship too. I can check on. Let's see what we got. Ooh, game design. You want to look at game design? Or let's do that. That sounds really fun. I think that's Professor Ashley. Did we rate her before? We might have rated her before, but it's still fun. Let's see. I'm all about game design. That's good stuff. Okay, we'll head on over that way. You guys say hi, and we'll have a fun time. I've got office hours after class till about 5:30. We can chat if you have questions about the project or anything in general. Let me know. If not, you take care. See you around.